Thank you. Good morning. My name is Jan Skowron, and I'm with the Ogle project. I will give you some things we were working on in 2018 and mention a couple of words about plans for 2019. So Ogle observes with the Atacama Desert with 1.3 meter Warsaw telescope. It is 23 years old already and is dedicated to our project all the time except the Chilean time. And we started observing microlensing in 92 with Ogle 1 phase of the project, and this is the sky coverage for this project. In the second half of 90s, we built our telescope and Ogle 2 phase started. Ogle 3 was early 2000s, and now we are in Ogle 4 phase, which is evolved to a large-scale sky survey for variability. For microlensing, we focus obviously on the most densest parts of the galactic bulge, but also we monitor more fields around. And this is actually one of the focuses this year was to start observations of this greater bulge region in order to get the idea about galactic structures from by looking at classical pulsators and other variability. This is a number of epochs we collected during Ogle 4 from 2010, and you can see it closely follows our observing strategy for microlensing, but also we have already gathered some quite substantial observations around. So typically, we observe microlensing with this cadence. The most dense fields and are red. And this year, 2019, we were observing as well and reporting microlensing discoveries with early warning system. But our second focus was to do this variability survey around. So we dedicated some of the time for this project. We still observed the whole season from the first to the last night of the season, but with a little lower cadence for microlensing. Second focus of this season was actually support of Spitzer campaign. When the Spitzer campaign was ongoing, we focused on early discovery of microlensing events and early characterization of them. To facilitate this, we narrowed a little bit the fields we were monitoring, but increase cadence and make the cadence a little bit more uniform. I will not go into details about this campaign. We will hear about the results from various other talks. Another highlight from the season was free-floating planet candidates with well-measured angular Einstein ring radii. So this event was the first one discovered in our database to have finite source effects. And the Einstein ring is actually 2 times smaller than the size of the star. What was realized, those events are interesting because you can measure angular Einstein ring. And actually, the nice thing is that the big stars are also the brightest. So we were able to do a dedicated search for all of Ogle bright light curves when we were able to push the amplitude limit down because we expect low amplitudes for those events, but the baselines are bright, so it's possible. And this search yielded 2 additional candidates. This one has an angular Einstein ring of the order of size of the source, and this one is very short timescale event with 5 times larger source size than the Einstein ring. So these are 3 candidates for free-floating planets, and with well-measured 3 angular Einstein ring radii, and this is not milliarc seconds, these are microarc seconds. and accordingly masses for those are quite small, with the first candidate in order 10 Earth masses or so. So our monitoring of greater galactic bulge and galactic disk, actually the early results are encouraging, and this year we increased the coverage even more. In the galactic disk, we widened the scope of observations as well, and this has some implication to microlensing. So now we observe the whole Magellanic system, galactic bulge, and this very wide galactic disk area. And we also, with this new data set, we are able to find the galactic microlensing events in the whole galaxy we see. And another great highlight from this season was we published the discovery of 2,000 new galactic Cepheids from this survey. And because they are classical Cepheids, we are able to measure distances to them and to make a three-dimensional map of the galactic disk. First interesting result from this is that when we look at classical Cepheids discovered by Ogle, you can see that substantial parts of the sample lies below the galactic plane. So this is a clear indication of galactic warp, and we've measured distances, we are able to make a three-dimensional model of the galactic warp. And it's quite substantial. At 15 kiloparsec from the galactic center, there are stars 1 kiloparsec below or above the galactic plane. So the warping is really substantial. And on the sky, it looks like this. When I draw a circles around the sun with these radii, you can see that any models predicting microlensing or that would like to analyze existing microlensing might take into account this warped model of the disk as well. Of course, additional thing is when we take out the warping, we can see clear flaring of the disk, so the scale height of the disk is rising as well, and it's well measured. As a bonus, we got the galactic rotation curve with well-measured distances from Ogle and supplementary proper motions from Gaia. It's possible to model the galactic rotation, and it's quite flat with a very slight slope down. So it also can be used for modeling of the galaxy. So for 2019 season, we are planning to continue monitoring of the inner galactic bulge for microlensing and issue early warning system alerts. If required, we also can support Spitzer campaign with early event discovery and early light curve characterization. And we will continue our observations of extended galactic bulge in order to get the Lyra stars and the galactic structure from those. We also will get CMDs and densities of red clamp stars to better model the galactic bulge, and we also will find much more variable stars. Okay, thank you. That is all.
So, any questions?
Why did you say if required for Spitzer? I mean, it's required. Yeah.
Okay. I didn't know that.
Yeah, it's urgently required.
Okay, thanks.
So I have one question about free floating planet candidates. So
Yeah.
I have impression that the source star for the free floating planet candidate is always very bright. Is there any reason for that?
Yeah, it's detection efficiency because basically the photometric noises are low and for bright stars, and it's but you can ask Przemek because he did the extensive detection efficiency calculations in this regard.
Did you?
Both the rope in the disk and the velocity that is when you go close to the center of the galaxy actually falls a bit below the expected rotation curve. Does all of this have impact on our Bayesian estimates for when we derive, the conclusions for Microlensing plans without full solutions?
Yeah, so the galactic surface data we have it's lacking inner 4 kiloparsecs. So actually, most of our models will yield lenses in this region. So this is still unknown, but so it's not super helpful. But it's still interesting to see it's such a consistency and quite flat and constant value here, and so there is some impact for galactic bulge events, but more it will be an impact for galactic disk events.
We have 40 seconds. Button.
Okay, can you go back to the plot where you show the variables and the one before where my question is, can you trace the spiral arms with the distribution of variables?
Oh, actually, we did model that, and the structures we see here were previously attributed to spiral arms. Okay. But actually, we have measured ages for those stars, and we were able. I was doing the model when we rotate them to the origin place of origin of those, and actually the spiral arms had different angle when the stars were born, and now after rotation, this is the ghost of a spiral arm, but it doesn't follow the gas spiral arm because stars rotate differently than gas. So these are traces of spiral arms at the birthplaces of those objects, but actually they were born here.
Thank you.
So it's time. So thank you, Jan.
Thanks.
So the next speaker is Takahiro Sumi. He's talking about prime.
Hi, I'm Takahiro Sumi from Osaka University. I'm going to talk about a PRIME project, the Prime Focus Infrared Microlensing Experiment. This is the first dedicated near-infrared microlensing survey. And the PRIME will support the double fast project by conducting the precursor observation and the concurrent observation. So the JAXA double fast study team is working on a Japanese community to join to the double fast. And we are considering these 4 items as a Japanese contribution package for the double fast. The first is we are providing the 100th nights of the Subaru time for the double fast Subaru synergy observations. The wide field imaging and the spectroscopic capability of the Subaru have a very good synergy with double fast. And so far, the director of the Subaru and the Subaru Scientific Advisory Committee agreed to commit for this commitment. And the second is the hardware contribution to the chronograph instrument of double fast. So we try to add the polarimetry capability in the instrument. And the third is that we are trying to provide a K-band data downlink station in the Japanese time zone. And fourth is that we are going to provide a ground-based microlensing data from the MORE project. And also the precursor and the concurrent ground-based infrared observation by the prime is also the one of the contribution. So as for the Subaru observation, we are having this double force Subaru synergetic observation workshop every year. And we just had the second one last December for discussing how to use the 100 nights of the Subaru time. And we will have a next one next November at Hawaii. So please join us to discuss what's the best way to use the Subaru time, especially for the making use of this for the microlensing double force program. So here's the objective of the prime project. The 50% of the time will be spent for the microlensing survey towards the bulge, mostly for the exoplanet search. And I'm going to discuss with this later. And other 50% of the time, we can do other sciences in the off-bulge season. So advantage of using the infrared is, as you know, near the galactic center and the galactic plane is highly obscured by the strong dust extinction. By using the near infrared, we can observe the stars near the galactic center and the disk. So we expect more stars in this area, and we expect more events and also the planet events. For this survey, we can measure the planet frequency near the galactic center, where the stellar density is much more dense than the other surrounding field where we are mostly observing currently in the optical. So we can compare the planet abundance in different stellar density fields, and then compare to if there are any effect on the stellar formation mechanism. And we are also trying to measure the map of the event rate in this region. That will be used for the optimization of the double force field. And we can conduct a simultaneous observation with double force to measure the lens mass. And we are also interested in the mass function in the galactic center. So this is the event rate map measured by the MORE. As you know, there is no data near the galactic center and also the galactic disk because of the dust extinction. So the prime project is trying to fill this gap and complete the event rate map. And this will be used for the study of the galactic structure, mostly in the galactic bulge. And also we can optimize the double force observation field. So we also try to measure the mass of the lens system by the simultaneous observation from the double force of the ground. This method can be already performed by the Spitzer and the ground. But the difference is the separation between the Earth and the Spitzer is about 1 AU. But the separation between the Earth and double force is only 1% of the AU. So for example, this event, August 2014, 124, Spitzer and ground-based observation found a time difference of the planetary anomaly of about 20 days. But this implies double force ground-based offset is about 4 hours. So this is very doable time differences. So we are ground-based observation by the prime and the double force. We try to measure this 4-hour difference. So this is the measurement of the parallax of the planetary signal rather than the stellar signal. And this method is the only way to measure the mass of the free-floating planet as well. So for the off-bulge season, we haven't decided what to do, but we have some plan. We can conduct a transit search for M dwarfs, and also the follow-up of the transient, like gravitational wave or high-Z GRB or supernovae. And also we can make some time for the double force calibration. And we will have a H-band spectrograph in our telescope, so we can conduct RV Doppler search for the giant planets around M dwarfs. This is the hardware contribution from each parties. The Osaka University and the Astrobiology Center in Japan, we will provide a 1.8 meter telescope. And the Osaka University will funding for the wide field imager. And the Dwarfs team will provide us 4 H4RG detectors. And the University of Maryland will manufacture the camera at the Goddard Space Flight Center. And the Astrobiology Center will provide a near-infrared high-resolution spectrograph. And this is the reason for the ABC joined to this project. And the SAO will provide the dome and building for us. Here is the current status of the 1.8 meter telescope. We have a base and the forks in the factory, and the other part of the telescope will be completed in a couple of months. And the primary 1.8 meter primary will be shipped in next May or so. And the total field of view of the telescope is about 1.5 square degrees. This is the 6th time of the full moon. And I think this is the one of the largest class field of view of this in the infrared for this size of the telescope. Here's the optical design of the telescope. So we will use 4 collector lenses, which made from the fused silica and all spherical. That makes every optics much cheaper. So here is the diffraction encircled energy distribution of the optics. And 80% of the encircled energy diameter is about 14 micron, which correspond about 0.7 arcsecond, which is small enough compared to the Median thing of 1.4 arcsecond at Sutherland. So we have finished manufacturing the corrector lenses, and currently they are doing the air coating. So we choose the bandwidth between the Z to H band. And refractivity, here's the simulation of the air coating refractivity. It's about 0.6%. So the total throughput would be about 94% for this optics. So for the camera, we are collaborating with Dwarfs. University of Maryland manufactured the camera at the Goddard Space Flight Center by using the 4 Teledyne H4RG detectors provided by the Dwarfs team. So this collaboration benefit for both parties because of this, our prime can conduct a near-infrared microlensing survey for satisfy our science interests before the Dwarfs. And then Dwarfs can get support from the prime, from the ground. Here's a schematic of the camera by the Yuki Hirao and Alex Kusher at the Goddard. We will use the 4 H4RG detectors under here. And we will cool the detector down to the 80K by using the 2 GT cryocoolers. And we will have a 2-wheel filter wheel inside the camera. And we will use the reach controller as a baseline for the reading the detectors. So we will have 2 cold filters within the duo. And each filter have 4 slots for the filters, but 2 of them are for open and 1 for the shutter. So we have a 5 set of the filters. And nominally, we are selecting about Z, Y, J, H band, wide field, wide band filters, and H band will be the primary filter for the main survey. And we are also considering the 1 narrowband filter, but we haven't decided yet. So if you have any idea what filter band and any suggestion, we are very welcome. And here's the schematic of the prime focus unit. Here's the corrector lenses and the focus mechanism, and the camera is attached. This system will be ready by next spring. Here's the schedule. we will install the telescope this year. And the camera development is a little bit delayed, but we are hoping to be installed in the early 2020, and we are planning to start observation in 2020. And also, after launching the double fast in 2025, we are conducting the concurrent observation with double fast, and we will continue to the end of the double fast. So here's a summary. The PRIME is the first dedicated near-infrared migraine exoplanet survey. So we try to measure the galactic distribution of the exoplanet. And we will complete the event rate map towards the galactic center to optimize the double fast fields. And we also conduct a simultaneous observation with double fast to measure the lens mass. And we will have a H-band high-resolution spectrograph in the telescope. So we will conduct radial velocity survey for giant planet. And we will have a TO observation for follow-up in any transient like gravitational wave and so on. And we are planning to start observation in 2020. Thank you.
So I had a comment about an additional use for Prime is actually developing models to characterize the W-first detectors. And the project is quite interested in this, and so they're hoping that they can have these Acadia chips ready so that you can read out the detectors with the flight electronics. And then also there's a thought that having narrowband filters in a gap in OH emission lines will allow us to get ground-based observations with moderately low background, a little bit closer to what W-first will see.
Yes, I don't know if can everyone hear me? Okay. So you mentioned that you're open to suggestions on a narrowband filter. And of course, every wavelength is its own special snowflake. You name a wavelength, there's a good science case for it. I'm wondering what are the criteria for the kind of science case you're looking for the suggested narrowband filter?
Well, there's no criteria. So whatever that we can conduct, we are welcome. But one point is we have a very the bright optics and the small f ratio. So it's not doable for very too narrow band because of the high angle, the incident angle to the filters.
I have one question. What's the cadence of the W first microlensing survey?
It's 20 minutes, 15
minutes. Then I think one of the major signs of a W first is that you said the time gap between ground-based observation and the W first is 4 hours. 4 hours. If the cadence is several several dozens per day, the caustic crossing structure will give you measurable give you enough time to measure masses. So you have to emphasize that.
Yeah.
You just mentioned that you show the in a finite size source event. So that is one case, but caustic crossing is very sharp. It will allow you to measure the mass.
Yeah, that's a good point. Yes.
So I have a question about you mentioned that the field of view of the telescope 1.5 square degree, but the backplate had much more places for CCD chips than 4. It looked like from the photo. So what are the actual field of view?
Yeah, actual field of view is about 1.3. So that 1.5 include the gaps.
Okay.
But we are dithering, or maybe not, but the physical size of the field of view.
So it's time. So thank you, Taka. So next speaker is Andy Gould, who is talking about upgrades for KMT net alerts, event finder, and data policy.
How do I advance the?
Okay.
So you're talking about some updates in KMTNet, which is a three-site survey, which originally was concentrated on 4 fields with low cadence support for Spitzer in 2015, but in 2016 has multi-tier of cadences similar to Ogle and MOA. And so these upgrades or updates are related to that. So the first thing is we've been doing for this 2018, we've semi-started Alert Finder. So basically 2 major reasons for this. One is Spitzer support to get augment Spitzer alerts. And the other is, okay, so what's the issue here? So most microlensing surveys in the southern bulge because there's less extinction, and so there's more cadence, so we find more events and blah, blah, blah. But from the standpoint of Spitzer, the northern bulge is just as good as the southern bulge, except you don't have as good light curves from the ground to compare to. But there are fewer alerts. So we'd like to, in 2018 especially, we tried to augment those alerts. The second goal is high magnification events. So this is typical old style survey plus follow-up high magnification event, some very low amplitude perturbation due to a Neptune planet in this case. And the original orientation of KMT was sort of to ignore these, not ignore, but anyway, not focus on high magnification events because if you have a random trajectory going through the Einstein ring, it's going to hit the planetary caustics more often than the central caustics. Anyway, the central caustics are okay, but nothing special. But there's a few reasons for changing that orientation. So first of all, the high magnification event detect all planets that are, and if you don't find any planets, it means that there's no planets. So that's a good way to find the planet multiplicity function from high magnification events. Much harder to do it from planetary caustics. Not impossible, but there's much less information. And so this is an example of, old event with, I think this Ogle 2008, 279. Anyway, so some huge zone of excluded planets. This is a major reason for trying to augment that. If we look at the historic cases of secure 2-planet detections and microlensing, both come from the era of survey plus follow-up. And you can see that we're missing now. We have 2006 and 2012. So there should have been one in 2018, and there wasn't. And probably the reason is no follow-up. So what are the challenges to this? For KMT, I mean, other groups are finding alerts, but we have very large volume, similar to when we're doing Event Finder. But we have to find alerts once per day instead of once per year. And we have to combine 3 observatories. So what's our solution? So first of all, we only look at recent measurements. And then we try to find 10 high sigma points somewhere in the recent measurements. And then go on to try to find same number of consecutive high mag points. The reason that we do this one first is just that we've eliminated 90% or more. We can do this. Doesn't seem like a very hard thing, but you have to sort all the points. And we have to look at it in 7 different combinations because one observatory might be having something wrong with it. So we'd have, there are 3 observatories anyway. There's 8 combinatorics, but one doesn't have any observatories in it, so we do that one. And then we fit all the data to a simple rising event. What's a rising event? It's a flat line and then a straight line up. So this is an example of such an event that was found by the Alert Finder. Then at the end of the year, there's a planet or possibly binaries. This has to be analyzed in detail in this event. So this is still not the highest quality light curve, but anyway, this is the routine pipeline. I'll show that more later. Okay, so in terms of the commissioning year, we only did northern bulge alerts. It's actually very difficult for us to set this thing up. We did have 20% of all Spitzer alerts. Here's the 2015 alerts and the 2018 alerts without KMT. And so KMT doubled the number of northern alerts. So that was our goal for 2018. And hopefully in 2019, we're going to have alerts all over the bulge. The improvement over other existing alert facilities, Vogel and Moa, is not going to be as great as in the northern bulge. But anyway, we hope to add some events. So second thing is an update on the event finder. Just to review how it works, instead of having searches of 3 parameters, we're searching 2 parameters. We use these Gould models from 1996. So this actually, with just one 2-parameter model, you basically can fit all light curves. It's as long as you don't go too far off into the wings. And we look at restricted domains. So in this case, we're looking at 10 times T effective. So you see, we just don't look at all this part of the light curve. Well, so that could be very important because there could be a variable star here or something. But anyways, the first cut, you can do this, and then you can try to figure out if there's something wrong with the rest of the light curve later. And by doing that, we can, let's see. Okay, another thing is we have augmented star catalog. So in the beginning, we were using Ogle 3 plus Dufault. The Dufault was pretty poor. That's over here. And then we augmented this with DCAM. So we have very dense catalogs now, although not exactly everywhere. So by adding this catalog, we added about 20% to our events in 2016. And we expect this will be typical for other years, but actually we're still trying to work on 2018. Another thing is we started to use filtered data. We get rid of the worst seeing and the highest background. I mean, this comes at some cost, and we actually miss a few events because of this. But we actually reduced the number of events candidates that have to be looked at by a factor of 7, so it's worthwhile. And the other thing is we have this Gould fits, but we've had Pachinski vetting. So it's overall more efficient. We can go down to lower chi-square. And so generally, we think that it's improving our event finding. So here's an example. This is something that was regarded by the Korean Army guy that we have working to find all these things for us as possible microlensing, not even secure. You see the data are quite noisy in the DIA light curves. So then this is the Pisces pipeline. That's anything that's regarded as possible clear microlensing is put through this Pisces pipeline, which is a lot better. And you can see here there's a planet. Can everybody see it? Right here. Anyway, so if you're like more focused on trying to find planets in this, you can notice that. And then you can run it through TLC pipeline, and here's the planet. So, so that's the different ways that we're going through it. Can find events pretty reliably by the DIA, but to actually find planets, we have to go to much higher technology things. And it's also finding binaries. Why does it find binaries so well? Why does Pachinski curve look like binary? Because it eliminates 10% outliers. So usually that's 10% crap, but in this case, it's 10% beautiful binary that gets eliminated if it's a Pachinski curve. Okay, so Jan has already talked about the free-floating planets. I just want to mention what we're doing about this. So this is, so he's already shown this. Here's a case of a free-floating candidate with finite source effects. So led Rose to do more extensive search that Jan already talked about, so I don't have to say much about it. I just want to mention that our alert finder didn't find any of these 3 events. So it didn't find this one because we weren't taking data yet. But it didn't find one of these other 2 because it was listed as a variable star, and the other one didn't fit our profile very well. So began working on, okay, so anyway, this is a motivation that, Jan has already talked about, so I won't go into it. But especially noting that that first one is basically flat top because rho is much greater than 1. So what's our attack? Okay, we want to look at 3 years of data. So we're going to only look at giants, same idea as before, and we're only going to look at short events. So this is going to reduce our viewing by quite a bit, amount of computer time, and we will not remove variable stars. So just by running a test thing that I'll show you before, we did actually recover those 2 test cases that were in the literature. So we're hopeful about it and find flat top profiles. So how are we going to do it? Here's the profiles we were looking at before. They're very good for Pachinski type events. But instead of doing that, do some flat top profile. So there's a couple of different examples here of what flat top profiles look like. And as I said, that it's found the 2 actual free floating candidates that were in our data that are known about. Okay, so new KMT data policy. All light curves from KMT discovered events will become public July 1st of the year following discovery. So for example, for 2018, we already have a bunch of alerts on the website, and we'll have the events that we're finding from the event finder hopefully soon. So you can look at those pretty soon, but you can start publishing papers on your own starting July 1st, 2019. Collaboration with KMT is welcomed, but not required. However, if you don't collaborate with us, you should cite our key KMT papers, but that's the only requirement. And if you're not, if you want to do your own TLC light curves rather than the pipeline reductions that we have on the website, if you show clear evidence of something going toward a paper, by that I don't mean a vague outline and hope and a prayer, but actual work, then we'll send you postage stamps so you can do your own reductions if you don't like our reductions. Okay, so that's it.
Questions?
What's TLC?
Tender loving care.
For 6 years, so with the new KMT alert and presumably very intense follow-up, how many multi-planetary events do you expect to find per year?
Well, I haven't calculated, but just based on the fact that our high alert events are actually quite bright and that we should be able to do much fainter events now, I guess once every few years, like once every 2 years or something, but I'm not really sure.
Yeah, so a few slides back, you said that you were not throwing away the light curves that are variable stars, and I'm just wondering why you would not throw those away since they take a lot more work and they're a small fraction of the total sample.
So this is only for the free-floating planet. We do throw those away for the major event searches. So typically what you find then is very long microlensing events that are actually variable stars. But if you're restricting your search to 3-day events, then variable stars will not produce those as often. But anyway, we must capture them. So there was one of the free-floating planet candidates came from a variable star. So all these huge stars are slightly variable, but they're varying on periods of 100 days.
I see.
If you concentrate only on the giants, the smaller mass planets may be, the magnification may be too small. Is there a concern on that?
Yeah, so we're, we have a special search only for giants, but we do have Event Finder, and presently our shortest effective timescale is 0.34 days. So we should be able to get down, 1/3 of a day. So we should be able to get down to quite short ones, but the normal case. But this is a special search for flat top things, which is where the giants come in.
We have another 30 seconds. So, quick question or comment? No? So, thank you, Andy. The next speaker is Yanis Sapras, who is talking about the Rome Layer LCOK project update.
Okay. I think I've got enough battery there. Should last me long enough. Okay, so can you hear me? Yes. Yeah, lovely. Okay, so I'm Yanis Sapras. I work at Heidelberg University, and I'm the PI of this ROMRIA project. So I'll These are all the people that are involved in the project, or most of the people. That includes also students. So from Heidelberg University, we have myself, Joachim Wamskans, and Markus Hundermark. From LCO, there's Rachel Sturid and Etienne Bachelet. From Salerno University, Valerio Boza. From NAC de Mao, Arnaud Cassan at IAP, and from St. Andrews, Keith Horn and Martin Dominic. Most of these people are here, so if you have any questions about the particulars of the project, you can talk to any of us. And there's also a bunch of students that are involved. Okay, so what is the Rome-RIA project? So we use the Las Cumbres Observatory network of robotic telescopes. Okay. But mainly the southern part. So we are running in 2 modes. We have about 2.3 thousand hours per year to find exoplanets beyond the snow line and study the demographics. So what's Rome and RIA? So what we do is we observe about 4 square degrees in the sky close to the galactic center. And the observations are performed in 3 bands, SDSS, G, R, and I. And our aim is to characterize the source stars, get more information about the type of star. Okay, so we have 24/7 coverage, weather allowing, from the southern LCO sites. Rome is, we use one of the LCO telescopes at each of the southern sites to perform observations every 7 hours of these 20 fields. And then it passes it on to the next telescope. So it's Chile, South Africa, and then Australia. And then we start again. And we also have a reactive mode, RIA. So this reacts when the event becomes highly magnified. It's a more complicated function than that, but generally, when the event becomes highly magnified, then one of the other telescopes switches to high cadence observation. So these are observations every 60 minutes for those events. Okay, so the aim, as I said, is to constrain the blended light. So if a microlensing event is unblended, then as it gets magnified, it's just going to go up and down. If it's blended, then it will be sort of curved, and we have lots of data points there on that curve, and we can sort of characterize the degree of blending. Okay, so here are the 20 target fields. How did we select those 20 fields? Well, we ran an algorithm. We started off with some random, rough positions close to the areas where the number of events was highest. And then we try to, with the algorithm, try to optimize the number of stars in each of these boxes, made sure they don't overlap, and also try to avoid highly extincted regions. Okay, so this was the final distribution we came to. Okay, so what's the expected yield? We simulated an entire season, a full microlensing season. The sampling was based on our observing strategy, which included noises due to weather and technical downtime based on our previous RoboNet project, so we had some idea of what this would be. The noise model was calibrated using observations from previous seasons, again with the using the RoboNet data that we had from before, and detection probabilities were evaluated after injecting artificial planetary signals. Okay, so what did we get out? We expected to have around 300 stellar microlensing events per year from Rome. About 50 of those would be observed in RIA mode. We're actually not getting about 50, we're getting a bit, a smaller number. But there are very good reasons for this, and we understand why this is happening. So we expect about 10 new planets in the data by the end of the key project, which is going to be in the mid-2020s, and we estimate that about 2 of those will be sort of in the Neptune range. Everything that we do in this project, including all the codes that we develop, is going to be released publicly. All the data, all the images, everything. So including modeling software, the pipeline. Okay, so here are the target fields from the first season, and you can see all the red dots. Oh, yeah, all the yellow dots show the events that fell within our survey footsteps, and there were about, as we expected, about 300 events. Okay, so this is a single field view, 26 by 26 arc minutes, 2 by 2, and then the microlensing event usually happens all over the place, actually. With Robin, we used to focus at the center, but now we can have a macrolensing event happen anywhere in the field. Okay, so then we do difference imaging on our images. At the moment, we're using our old pipeline while we're still developing and debugging the new pipeline. I'm going to say a few things about that. But basically, the idea is you have your target star, okay, it gets brighter. You have a reference image, which you match to all of the other images, and then you subtract them, and you have a residual there. So anything that doesn't vary is flat, it's just noise, and everything that varies just leaves a residual, and that's what you measure in the end. Okay, so as I said, we are developing a new pipeline. This is based in Python, and it's going to be open source. So we already have done all of these bits. So the reference image is produced. We can identify all the stars in the reference image and do some basic PSF fitting photometry. We can geometrically and photometrically align the reference with all of the other images. We can do the difference imaging, and we can extract light curves. So why are we not using this full time? Well, we are still working on refining the photometric data quality before we do our first data release. So this still needs some work. I mean, the quality that we're getting is not as high as we would like. So so what fails is that when the image is worse than the worst expected full width half max over Strel ratio, the reduction is not very good. It also fails when the astrometric solution, because of the telescope jitter, of the pointing jitter, is not so good. So I'll show you some examples now. Okay, so if you have a reference image here, for most of the images we get a clean subtraction, but occasionally if one of the images has irregular full width half maxes, the distribution of the full half maxes is a bit strange, then we cannot use the same U matrix throughout the image, so it does leave residual. So we're trying to optimize that, and also when there's weak alignment, you get this usual sort of bipolar, I would say, sort of negative positive subtraction. So obviously the photometry then is not so great. So this is what we're working on improving right now. This is the most challenging part at the moment, I would say. Okay, so we did some test reductions with our previous pipeline, and this is kind of the data quality that we get. This was just point source point lens event from the first season, and we can sort of we can identify the source type here on the color diagram. Here are some binaries from the 2017 season. This is work that Valerio Boza is doing. These are 4 of the events that he's working on from our 2017 season. We also have 0022 from this season, which is a paper that is almost ready for submission by Rachel Street and Etienne Bachelet. So this is modeled by Pi Lima. We have lots of data covering the caustic crossing there. And we're also planning to run machine learning algorithms to identify events in our data set. So this is, for example, how we plan to do it. So this is one of the light curves that we have from 2017, and here's how the algorithm kind of develops. So we can run it in real time. We can identify events in real time, and you can see here at this point the interpretation that it is a macrolensing event sort of is the most likely interpretation. Then there are some data points that are a bit dodgy, so it goes down, but then it's pretty certain that it's microlensing. So this is work done primarily by Daniel, who is one of Etienne Bachelet's students, and we're developing this further. But it was some tests that we ran on one of the survey fields proved to be quite successful. It recovered almost all of the microlensing events there. Okay, so these are all our observations, ROM plus RIA from 2018. You can see the distribution in all of the different sort of fields. And here you can see some over-dense regions. These were the high magnification events that RIA picked up. And there is an excess here on field 16. This is where 0022 was. and 0022 was also very bright. So RIA had it very high on the observations list for a very long time. What about our average image quality? It's still not perfect. For some reason, the LCO telescopes are not, I mean, we are getting sharp images, and our best site is in Chile, but we're still not managing to get the quality that we kind of expected. So there is, LCO thinks, so they are aware of the issue, and the focusing problem seems to be due to some software, or it could also be a mechanical problem. But they can certainly deliver, telescopes themselves can certainly deliver sharper images. So we're trying to see when this issue is going to be improved, but it's on LCO's plate to deliver that. Okay, we also have done a lot of work on developing a front end for, I mean, we're an international team, and we like to keep in touch, and everybody can be aware of what is being done at what point. So we have a database front end, and you can see which telescopes are open, what they're doing, our software, what our software is doing. There are event dedicated pages, sort of what exposure times we're getting, when the observations were submitted. So we can trace back everything throughout the project. We know what was done when and exactly. So it's a very well characterized project. So if we want to run simulations of it afterwards, we can do it, and we can compare it with what we're getting. And here are the relative priorities for RIA, what it's actually observing right now. If you click at any of those points, it'll just give you it'll take you to an event page with the latest updated parameters. It'll do the fit on the fly for you if you want, and plot the light year for you. And there are buttons to just download all the data, and if you want to, do the fitting yourself and everything. So these are all within the collaboration that anybody has access to these pages. Okay, so I think that's it. I'll stop now. Thanks.
So any question or comment?
How deep are you getting in G and R band?
How deep?
How deep, yeah.
So we expect to go, so right now, I think it's around 18.5. I think by the end of the project, we'll be able to go 19.5 to 20 maybe. But the G band is very, very difficult. I think we'll probably have good enough data for only the brightest of targets, sort of the brightest 40% of all events. David.
So I was a little confused as to why your follow-up program only has a cadence of 60 minutes. That seems too short too long a period to be able to see caustic crossings for main sequence stars. And if you look at a lot of the published high magnification planets, right, it's pretty clear that they wouldn't have been discovered with 60-minute cadence.
Okay, I didn't mention that it has two modes. Okay, one mode is the default mode, so it goes to 60 minutes. And there's another anomaly mode. So once an anomaly is detected, well, this hasn't been implemented yet, but it's on the plan to do it. As soon as there's an anomaly detected, then we go on it and we hammer it every 15 minutes. So the reactive mode has time allocated to it for the 15 minutes cadence as well. So if an anomaly is hit, we have software already that can detect those, and it can go and start observing in 15 minutes, every 15 minutes.
A comment on your difference imaging,
yep,
right? And the example you showed on the right, it's not actually a misalignment, it's an insufficient kernel degree. So you may actually...
So over here, you mean okay. Well, okay, I mean, we can talk about this offline. With Marcus is the one that's working on this, if you remember from the last meeting. But yeah, we can talk about how we can improve that.
Quick question. What that acronym ROM and RIA? ROM, you are from Greece, but that's not the reason. Okay,
okay, so ROM is Robotic Observations of Microlensing Events, and RIA is Reactive Event Assessment.
General fields, you have 7-hour cadence, but with the LCO scheduler that we all know that sometimes have problems, what is the actual cadence of multicolor observations, and how does that compare to the Ogilmoa KMT?
So it's pretty much 7 hours. So we do GRI, 20 fields, then we go to the next telescope, GRI, with each field, so it iterates over each field. And as you can see, sort of the distribution in the end, it's it looks like it's sort of evenly distributed. So we are pretty happy with it. So it is working.
It's time. Thank you, Yanis.
You're welcome.
So the next speaker is Andrei Kohl, who is talking about the 2018 microlensing season at Utah's Green Hill Observatory.
Pointer. Thanks. All right. So, yeah. Thanks for the invitation. It's a pleasure to be here to tell you about challenging, but I think ultimately really successful 2018 season in Tasmania and our plans for 2019. Obviously, there's a lot of support and help that goes into this. Most of the observations we did this year were done by myself and Kim Hill and Jean-Philippe Beaulieu, supported in Paris by Christian Couture. And we used a lot of the infrastructure and software that was legacy from the old Planet project. So many people in this room will have been involved with our data processing. I'd particularly like to call out our PhD students in Tasmania, Josh Blackman and Katie Vanderoo, who are working on the modeling. And you should listen to Josh's talk tomorrow about some of that work. So the advanced slide is somewhere. Okay, thanks. So yeah, for those who don't know, we've been doing microlensing observations in Tasmania since about 1995, starting at the 1 meter telescope at Mount Canopus, which was just a little bit outside of Hobart. But a few years ago, we started building a new observatory site that we named in honor of John Greenhill, located at Bisdeetir, up about an hour's drive, a much darker site and one where we could plan for remote observing right from the ground. The photo's a little out of date. Now, if you went there and looked, you'd see a 6 meter radio dish that's used for SpaceX telemetry to their Dragon capsules, and the beginnings of a clamshell for a 50 centimeter telescope that's going to go in later this year. So just sort of the quick hit, the 2018 season was in many ways similar to our 2017 and 2016, with the exception that we have now got fully remote operations. So we save ourselves a couple hours of driving each way. And in fact, the weather was a little bit better this year. So there's a typical sort of light curve that one of my students produced in 2016, and I'd just like to reuse the figure because it's a pretty one. But we still have a couple of observers working in follow-up mode. And one of the things that we are a little bit unhappy with was that we're still working with a relatively small field of view. It's a reliable camera, but it is quite old and quite small. Typical seeing is around 2 arc seconds with a distribution from around 1.4 to around 3.5. One of the problems we've encountered is that there's a sort of major optical flaw in the primary mirror. And so all 2018 we operated as basically a 1 meter telescope, or maybe even a little bit less. So there were a number of problems with the telescope as delivered. In particular, it didn't really hold collimation very well. Lots of sort of tracking issues. And once we got those sorted out, we realized that, in fact, the point spread function looks something like that. So that's a stack of 13,000 images of a 12th magnitude star. So the little core in there is a couple of arc seconds, but we have scattered light, really asymmetric, nasty astigmatism going out to about 8 arc seconds. But if I cover the outer sort of 4 to 6 inches of the telescope aperture with something sort of rigid but lightweight, we get a very nice, circular, beautiful point spread function at the cost of some sensitivity. I'll get back to this later. That was our solution for this year, and it worked quite well. We got very nice error bars on some crowded field photometry. So just wanted to So again, we've been responding mainly to MOA and OGLE alerts, but if you have any event that seems high priority, you can shoot myself or Kim or one of us, Jean-Philippe, an email, and we'll get on the sky as soon as it's clear and follow up at very high cadence. Our photometry is done in basically real time using Michael's PYSIS software and transferred right away to the old Planet servers in Paris and updated a few times a night by sending them over to St. Andrews for publication in the Artemis system. In 2016 and 2017, we had very few observable nights due to really high humidity because of La Nina weather pattern. But in 2018, we kind of avoided that, and we sort of had much better conditions and a lot of observable nights. So we followed 53 different events over 76 parts of 76 different nights, which is quite a strong increase, and it's our best season yet with the new telescope. So not so new anymore, but finally kind of producing data the way we wanted to. And I guess the big difference is that we can do it from campus now in the relative comfort of our own offices. And in principle, you could do this from anywhere in the world if you had the right access through the university's firewall, which is not always easy to get. So I'll just give a couple of highlights of some of the events. Again, if you're analyzing some event, just check with me or one of the other Tasmanians, and we can tell you if we've got data on that event. So this was events we fed through to Artemis and was picked up by Valerio's real-time model. If you're curious, we're listed as B and C I-band in Valerio's real-time model. This is just showing the really high cadence and good photometry quality in a high magnification finite source event. Not much sign for any asymmetry. We probably need to re-reduce some of our data down in the falling part of the light curve there. But we had basically continuous coverage with a 3-minute cadence over that event because it looked like our best target on that particular night. So disadvantage is we have to be there doing the observations. It's not robotic. The advantage is we're pretty responsive to be able to follow up very high magnification things or any sort of anomalies. So there are some other events that may or may not have some planets in them, and we're eager to work with as many people as we can. So just one other event that we monitored at the end of the season. This was in the Large Magellanic Cloud. We managed to get V and I band exposures, so I sort of created a nice false color image of it. It's red giant in the sort of northern part of the bar of the LMC, and we followed it over most of a month, basically every clear night. And it's possibly interesting because it's in most of the surveys of the LMC, so there are about 11 different photometric measurements of the source at baseline to work with, so we could potentially characterize that really well. And here's just an example I pulled off of the old Planet page, just showing the MOA data. And at this point, we realized this thing might be worth following, and so there's our data. It's a little bit faint with our masked aperture, but we hope to be doing better in the future. It's kind of a shortish time scale for an LMC event, I think. And again, not much sign of an anomaly, but it could be interesting for studies of galactic structure and LMC structure. So it's still very much just showing some of the data, not really doing much of the analysis, because I want to have time to describe what we're looking forward to is better point spread function and unmasking the telescope to use a full aperture. And it turns out that it's easier to buy a whole new mirror than it is to take a 50-inch mirror out and send it to be refigured in the outer regions. So we managed to convince the university to buy us a new 50-inch mirror, which I'm not quite sure how we talked that quickly, but we did. This is the mirror a few days ago, just after the polishing has been finished, figuring has been finished, ready to go into the final polishing. you might be able to see from that picture. You can certainly see from this picture. It's got a kind of an interesting structure. It's been made lightweight by, it's constructed with a couple of hundred Pyrex posts sandwiched between two plates and then slumped in a kiln to approximately the correct paraboloid and then figured into a rather steep hyperboloid after that. So it's a little bit experimental, but it's only going to weigh a third the weight of our current mirror, and we're expecting to get that in May of this year. We were expecting to get it in February this year, but the first shipments of glass from the supplier apparently shattered in transit, so we've pushed everything back by about 3 months. So we hope to be in operation kind of at the end, if we're lucky, at the end of the bulge season this year. We're not likely to be on the sky in May or June to do any lensing. So this is just a few weeks ago, removing our old 50-inch mirror, lowering it down. There's Kim Hill, who's been responsible for a lot of microlensing observations and a lot of our computer support. If anyone wants a 50-inch mirror that needs some refiguring, we've got one. We know where to find one cheap. So just to summarize, we're fully remote. We're able to respond within 7 minutes. If you email me and I'm online, I can get to the observatory and be on the sky in 7 minutes. Yeah, we'll probably have less than 53 events observed in 2019, but by 2020 we should be back with a brand new mirror. Just the last sort of final thing to mention is that we won't be completely off the sky in 2019 because we're putting this 50-centimeter telescope up it should be installed in March of this year. It's an RCOS 20-inch, so quite a bit smaller, but able to follow bright events. So again, we'll keep watching the alerts and keep sharing our data sort of the same way. So thanks very much for that.
So you mentioned there's a radio dish that was put next to the telescope. How much observations?
It's down the hill a little bit, so it's less than 20 degrees above the horizon. Not a problem at all.
Well, for some reason, I thought that you had the old Ogle 3 camera, which I thought was 8K camera, so that's not true.
Well, that was a plan, but it never came to fruition. Yeah.
And then another question, so do you have data on MOA 2018 bulge 241?
I have to check.
Original mirror?
Sorry?
Could you remind me the vendor of the original mirror?
Okay, that's a long, long story. The mirror itself was made at Corning in 1972, and then sat in storage for 40 years, and was then acquired by a Canadian amateur astronomer and businessman who donated us the telescope. And he hired a couple of different opticians. So I probably shouldn't name names given the status of the mirror for the recording, but we can talk over the coffee. But it wasn't a let's put it this way: the 50-inch was by a factor of 2 the biggest mirror that optician had made up to that point.
Any other questions? So thank you, Andrew.